Alrighty, folks, welcome back. This is going to be lecture number 3, part 2, or part B, however I label this. So this is jumping into the second lesson of module number 1. So we'll finish up the first part of this, which is kind of the randomized block design. That's what we're going to be starting with, and then the next lesson, which will complete all of module 1, will be the two-way ANOVA. So let's jump into this. So as I said, we'll be starting with randomized block design. So this is going to be just a very, very slight tweak on what we did with the one-way ANOVA. So remember back with a one-way ANOVA, what we were trying to do is we had one factor that had multiple different levels, and we were asking the question, is one level better than the other for affecting the response or the outcome of this? So in lesson 1, we learned how to use a one-way ANOVA to analyze data obtained from a completely randomized design, again CRD for short. Just a quick definition here because this is going to play a crucial role as to the lead into what we're going to do next here. So a completely randomized design to compare P treatments. Now again, our example that we had last class was dealing with the 3 different types of gasoline. So there was 3 different treatments in total. So P treatments in general is one in which a group of N, and here is the key part that distinguishes really the difference between the two. We have N, the number of experimental units. These have to be relatively homogeneous, which basically means the ability of each one has to be relatively the same. So if we think back to the gasoline example, and this is kind of what the problem I have here is afterwards. So I'll jump back into the definition just in a second, but let's look at the problem here. So from our last lesson, consider the gasoline example where 5 cars were assigned to each type of gasoline, and we were looking at the effects on mileage. So which brand of gasoline had better mileage for the grouping of cars. Now suppose that a sample of 15 cars, the ones that we had for the experiment, so again 5 for each, some were naturally better at gas utilization. So that means it doesn't matter which brand of gasoline, these cars were going to run better regardless. So there is an inherent bias that is already in the experimental units, which we weren't able to detect the last time we did this with a simple one-way ANOVA. So we need to change this a little bit. Continuing on with this, so the difference in ability can cause the within treatment variation to become quite large relative to the between treatment variation, causing the failure to reject H naught. So remember when we were looking at that ratio between the two, or ratio of the averages between the two, we were looking at the between treatment, so how far away is the average of each treatment from the center, versus the within treatment, which we were basically looking at how good is that center at explaining the variation in the treatment itself. So if all of the treatment outcomes, for a specific treatment, if all of the outcomes were very, very close to the center, then the center would be a good representation of the outcome. But on the other hand, if we had a treatment where we had the center and then there was observations far to the left and far to the right, well, maybe that center is no longer good at being a representative for the entire treatment in itself. So if we have this inherent bias in there, what we're doing is, again, we are adding more variability that we can't really understand in that within treatment. So that's our denominator. The bigger the denominator is, the smaller our overall ratio is going to be, and the smaller our ratio is going to be, the less likely we are going to reject the null hypothesis. So adding that bias in there automatically lessens the ability to reject that null hypothesis. So that's because, again, what we need is that relatively homogeneous experimental units. And of course, as I continue with the definition here, are randomly divided into P subgroups. Again, those are into the 2 different treatments. All experimental units in each subgroup receive the same treatment, with each treatment applied exactly once to that subgroup. Yeah, so that's basically all that means. So, sorry, 1 second here. Yeah, so that was the issue. Okay, so how do we correct for this variability or this bias that we've now added into the experiment? So to mitigate the effect of the extraneous factors on the response variable, we employ what's known as a randomized block design, or RBD for short. So here's the definition of a randomized block design. So a randomized block design containing B blocks, not treatments, in this case we're talking about blocks, and P treatments consist of B blocks and P experimental units each. Sorry, of P experimental units each. So what I'm basically saying is, instead of breaking this down by treatment and assigning experimental units to each treatment, we are building these blocks. And each block is going to contain P experimental units, again, the number of treatments. So basically, what we're saying is each block is going to contain all of the treatments inside of there. So these treatments are randomly assigned to the units in each block. So we have the P experimental units. We'll randomly assign which order they go in, with each treatment appearing exactly once in every block. So basically what we're doing is we are creating these blocks, and inside every single block, every treatment possible is going to be there in some different order. Now, how does this help us? Well, we'll get to that point in just a second. But what we're going to be doing is we are going to be able to control that level of variability now that we've added in, that maybe potential inherent bias that the experimental units have. All right, so an RBD, so a randomized block design, is like a CRD, a completely randomized design, because it focuses on a single factor of interest. So this is the key part here. I'm going to underline this because I don't want anyone to forget this. We're still looking at a single factor. So we've created these blocks arbitrarily, not arbitrarily, but artificially. That's a better way of putting it. We've created these blocks artificially. We are monitoring how they are going to behave. But again, what is of interest to us is the single factor and how the different levels of the single factor affect the response variable. That hasn't changed, staying 100% the same. However, unlike a CRD, so again, completely randomized design, a randomized block design includes a second factor called the blocking factor. So it does contain a second factor inside of there, but again, the key interest for us is just on that single factor and how, if we vary that over the different levels, how that affects our response. And that's kind of what I'm saying down here. A blocking factor is a factor that the researchers control in order to reduce the within treatment variability. There we go. But here's the key part. It is not the primary factor of interest. We are going to be testing it. It's going to be telling us whether or not it was appropriate to do a randomized block design. But at the end of the day, I don't really care about that aspect of things. It's just helping me understand the variability within treatment variability, so thus being able to build a more appropriate test statistic to, again, be able to either fail to reject or reject the null hypothesis. All right, so just a little bit of information here. So the levels of the blocking factor are referred to as blocks. Straightforward. A randomized block design compares P treatments by using B blocks, as we've already said in that definition. Each block is used exactly once to measure the effects on each treatment. So every single block sees every single treatment. The order, that's different. That's going to be randomized, but it sees every single treatment. So as a result, the total number of observations that we are going to see at the end is, if there is B blocks and each block contains P different treatments, B times P is equal to N, which is the number of outcomes we are going to get for the response variable once we initiate this experiment. All right, so the P experimental units within each block are typically homogeneous with respect to other factors that may affect the response variable. And that's, again, the key part, that if we are using multiple ones in there, we want to be able to not add any additional bias that we don't want or that we can't measure. So how do we do this? How do we use these blocks to control? Well, there's a couple of different ways of being able to do this. If you're taking another course, so if you're taking our STAT 3504 course, I believe, memory serves me correctly, again, you'll be seeing all of these things in much greater detail. We're going to be going with the most basic of them all, which is we're going to use a single experimental unit to obtain all the responses of a given block. So what that means, if we think back to our gasoline example, what I'm going to do to remove that inherent bias of that potentially a car would have better gas utilization than the others, what I'm going to do is I'm going to create a set of blocks, and each block is going to see all three different types of gasoline. Now, I'm not going to assign three different experimental units to each one of those blocks. All I'm going to do is assign a single experimental unit, so a single car to each one of those blocks. So instead of having, say, the 15 cars in total, what I may have in this case is, let's look at 5 different cars, and those 5 different cars will see each different brand of gasoline. And then from there, we can still test if the brand of gasoline will, if one is better than the other in terms of affecting mileage. But you're also going to see how we would be able to see if there is some inherent bias in the terms of the car's abilities. Another way of doing this, which we are not going to be talking about, but I thought I would just bring it up anyways because it's good measure to do so, is using similar or matched sets of experimental units within a given block. So again, just trying to make it as homogeneous as possible. All right, so treatments are assigned to the experimental units at random within each block. So that's why I said each block will see every single every single block will see every single treatment. The order in which those treatments are applied is random. All right, so let's just kind of go with a quick example of where we may want to use a randomized block design. So in this example, the manager of a fast food restaurant wishes to assess the efficiency of 3 kitchen designs for assembling menu items. So say like a McDonald's or something along those lines. They are looking to redesign their kitchen because they want to improve the efficiency of their staff within that. So they come up with 3 different designs. So if we were using a completely randomized design, a manager could assign independent random samples of employees using each design. So for example, what we could say is if there's 3 different designs, we are going to select from our pool 7 employees to do each one of the designs. So we'll say we have design A, B, and C. We'll have 7 for A, 7 for B, and 7 for C. So in total, there will be 21 experimental units. And then, of course, each one will kind of go through and we will be able to get an average for each one of the kitchen designs. And then we can see at the end of the day, well, which one is better. But of course, we have to now sit back and think, is this an appropriate design? Or is there some inherent bias that could potentially happen? And really, anytime there is a human aspect to it, we really should be asking this question because, of course, something could come up that's going to influence the design of this. So let's suppose that, a group of the employees, they could have been your A team of the employees. These are the best ones. And it didn't matter which kitchen design that they were in, they would be able to excel no matter what. And if that's the case, we have that ability within our group. Our total group is no longer homogeneous. They all don't have that same ability. And that inherent bias is now inside of the experiment. So just kind of as a note here, however, because employee ability could differ substantially, it may be difficult to identify any differences between the efficient methods or the efficiency between methods, or in this case, between the kitchen designs. Now, if we take that similar approach, but this time under a randomized block design idea, the manager would say, let's only select 7 employees. Each employee would represent a block, and each block would see each one of the treatments. So each of those 7 employees would see each one of those different designs in potentially a different order. Not potentially, in a completely random order. There we go. All right, so let's build the foundations for this. Now we're talking about a one-way ANOVA with blocking. Again, the idea is still it's a one-way ANOVA because there is a single factor that we are looking to see. Again, if we vary those levels of that factor, do they affect the response variable? But we want to control that inherent bias that we're adding in because of the experimental units, so we're adding blocking. All right, so in a randomized block design based upon, again, P treatments, B blocks, each one of the B times P combination of treatments and block component and block corresponds to a population of potential responses. So we observe one value of the response variable for each one of these B times P populations. So again, the general idea of this is excuse me, exactly the same as before. We have an experimental unit. It goes out, it does one of the different treatments there. So there's a B times P possible or total, again, number of resulting outcomes from the response variable. And these come from a population which we'll see is going to be, or assumed to be, normally distributed. So as before with the one-way ANOVA will allow us to estimate and compare the effects of P treatments on the response variable. That's the key part, not the blocking part. That's the key part. However, it will allow us to estimate and compare the effects of the B blocks on the response variable. So on top of that, we will be able to come back and see, is there an inherent difference within these blocks? Again, we are assuming that there is going to be some level of variability between the blocks. Not each one is going to be perfect. So the question becomes, is it statistically significant? Is that difference really a meaningful difference, or is it just based upon the fact that I grabbed a random sample and we knew this was going to happen? That's what we're testing. That's what our hypothesis test is going to be. It's exactly the same as the one-way ANOVA. We have our primary factor that we are looking to vary, and at the end of the day, we expect to see some level of variation, but is it statistically significant? Is it greater than our alpha? Does it fall into our rejection region? That's what we're asking. So here's our hypothesis test. So with a completely randomized design, our main interest, there we go, helps if I read this properly, as with a completely randomized design, our main interest with a randomized block design is to perform the following hypothesis test. So again, this is on that primary factor. So what we're asking, our null hypothesis, no difference exists between treatment means. So again, this is our mean of, say, treatment A has to be equal to our mean of treatment B, which is equal to our mean of treatment C. And the alternative hypothesis, the one that, we're saying that there is a difference. Again, we don't know where that difference is going to be, but we do know that there is going to be a difference if we're able to reject the null. We're saying at least one treatment mean differs. So that still hasn't changed. That is our primary question we want to be able to answer here. But now we also have a hypothesis test with the blocks. And again, for us, each block is going to be represented by an experimental unit. That experimental unit will see all treatments just in a completely randomized order. So our null hypothesis in this case, very similar. Again, we're talking about the mean. So we run the experiment, we record all of the outcomes for that experimental unit or that block, and we can take an average for that block. And so we'll have an average for the first block, average for the second, average for the third, all the way up to however many blocks that we have in total. That is B, subscript B. So the null hypothesis is no difference exists between the block means. So again, the mean of B sub 1 is equal to the mean of B sub 2, which is equal to the ... equal to the mean of B sub smaller b. There we go. And of course, the alternative is at least one of them is different. We don't know which one, but if we do reject the null hypothesis, then, if we're thinking about the car example, then at least one of the cars operates better regardless. Same as before, underlying assumptions that need to be met and can be verified in exactly the same sort of way. So in order for a one-way ANOVA with blocking to produce valid results, the following assumptions must be met. Random assignment. So we've obtained responses through randomized block design, where each of the B blocks receives all P treatments, but in random order. Again, the normality. So each one of those responses, each one of the outcomes we get from the experiment needs to be coming from a normal distribution. Constant variance, same idea for each one of these outcomes. That's exactly what we are expecting to see. And yeah, those are our three assumptions. So really no difference than what we were doing with the one-way ANOVA. All right, a little bit of notation here. Just a little bit though. So we have two subscripts. So I have I and I have J. I'm indexing I starting from 1 going all the way up to P. So that is going to be for my number of treatments, no difference there. And J is going to represent my blocks. So index starting at 1 going all up to small b. Same as before, there's an xi sub j, which is going to be the response or the observed response under treatment I and block j. again, we're breaking this up into two different things. So we're breaking this up into treatments, and then we're going to break this up into different blocks. So we're going to look at all of the different treatments regardless of blocks, and we're going to ask, well, what is the average for that treatment? So the little dot afterwards, after that subscript I, just basically refers to the fact that I don't care which block it's in. I'm just looking for all outcomes from that specific treatment. And then we'll do the same thing in terms of the blocks. I don't care which treatment, I'm just focusing on the block. So we're going to have an average outcome in terms of the treatment, and we're going to have an average outcome in terms of the blocks. And of course, same as before, we're going to have the average of the entire experiment. That is just X bar. So again, we have our total variation, which we are going to look to break up into, this time, 3 different components. One component in terms of the factor, the primary factor that we are looking to evaluate, one in terms of the blocks, and then the last is just going to be the error, the things that we cannot explain. So how do we calculate the total variability in this case, or the total sum of squares? Same as before, what we are going to do is we are going to look at every single outcome that we've got. So we've ran the entire experiment, we've collected all of the data, and we're going to look at, well, what is the center of this experiment? And then I'm going to take each one of the outcomes and say, how far is it away from the center? So here I just have I have a double summation, but all I'm doing is I'm saying I'm looping over each block, I'm looping over each treatment. So I'm looking at every single outcome that we potentially had from running, or every outcome that we did have from running this experiment. That's our xi sub j. I'm subtracting it from the center of the experiment, so I'm getting the distance away from that. I'm squaring it because I want to make it positive. I don't care if it's to the left or to the right. So squaring it makes it positive overall, and then I add them all up. So that's it. I run the experiment. I have my data here. How far is each data point away from the center? Square it, add it up. That's my total variability. As I said, we're going to break it up into the 3 different parts. So one is the treatment sum of squares. So again, in terms of the primary factor, then we're going to be looking at the block. So the block sum of squares, and last but not least, the error sum of squares. So if we decompose that formula and we break it up into the 2 different parts, one where we're focusing on just the blocks, one we're focusing on just the treatments, I have the 2 different sum of squares. Again, I'm not going to ask you to memorize these formulas. I want to tell you where they're coming from. I'm not going to ask you to memorize them because, again, we are just going to generate all of this data from R, but it's good to know where they come from. So the SST sum of squares for the treatment, we have a total of B blocks, so I'm scaling everything by B. I'm summing from I up to P, so I'm going over all the possible treatments, and I'm saying what is the average for each one of the treatments minus the center of the experiment and squaring it all. Same idea for the sum of squares for my blocks. I have a total of P treatments here, so I'm scaling it by P. I'm indexing starting at 1, going all up to the number of blocks, and I'm saying, well, what is the average for each block minus the center, and then again squaring that after, adding them all up, and that's going to get me the sum of squares. Now, last time I did have this nice little formula for calculating the error. I don't in this case, but what I do have is a way of being able to calculate the total. So SSTO, I can calculate the treatments SST, and I can calculate SSB. So if I just rearrange this formula, so I'm moving these 2 to the other side, I then isolate for my SSE, my error, which is just the total minus the sum of squares treatment minus the sum of squares blocks. All right, so we know how to calculate all 3. Perfect. That's going to help us start building our ANOVA table. And then once we have that, the degrees of freedom, everything else, it will all fall into place. So let's start working on an example, which we will carry over for the rest of this lesson here, which in this case is kind of close to being done. So this is the exercise that we are going to be focusing on for right now. So to compare 3 brands of computer keyboards, 4 data entry specialists were randomly selected. Each specialist used all 3 keyboards to enter the same kind of text material for 10 minutes, and the number of words entered per minute were recorded. Okay. So we have, what are we trying to do at this point in time? That's a good kind of first question. So we have 3 different brands of keyboards. And what we're looking to do is we are looking to determine the efficiency. Is one keyboard better than the other at being able to enter more words per minute? So instead of like we did with the gasoline example where I could find 5 different data entry specialists, assign it to the first brand, 5 different to the second, 5 to the third. Again, we run that risk of that inherent bias that, some people are just better regardless of what keyboard they're using, or worse regardless of what keyboard they're using, and it's going to influence that within treatment variability. So instead, because that bias is potentially there, we build blocks. So each block in this case will be an experimental unit. Our experimental units are our data entry specialists. So I have 1 block, 2 blocks, 3 blocks, and 4 blocks. So this is my blocks. And again, each block sees each brand of keyboard, or each treatment in this case, which is each brand of keyboard. Now the order that we do this in, we don't know. It just has to be random. So the first block may see A, B, C. The second may see B, C, A. The third might see A or C, A, B. Again, it's just going to be randomly assigned. So what you can do, and again, I'm not saying you have to. We have the formulas to be able to do this. We have the data here. If you want, and I'm not going to do this, but I suggest maybe do this once because this is a nice small example. Calculate SSTO, so the sum of squares total, the sum of squares for the treatment, the sum of squares for the block, and then rearrange this all and get the error term. Just so again, you're comfortable with this, you see where all of this is coming from, and hopefully that solidifies, there we go, exactly what we're trying to accomplish here. We will be doing all of this in R, all the calculations will be done for us, so you'll have a way of being able to verify if you did the calculations correctly. I think that's the big sort of difference here between this and the 2601 or your first stats course, because at least the way we do it here, the first stats course, you'd be doing a lot of this by hand. In this case, once you see like even this one, this isn't too bad, but when we get to the two-way ANOVA, you don't want to be doing these calculations by hand. That's why we have R to be able to do it. So as long as we understand what's going on and can understand the output and again how we got there, we can save our time by not doing those calculations. All right, so same as before when we were building that test statistic, what we were focusing on was not the sum of squares for each one, but the average sum of squares, so that mean square. So we need to be able to take these sum of squares and divide it by the correct standard, or standard deviation. Degrees of freedom, that's the word that I was looking for, not standard deviation. That's not even close to right. If I was going to edit this, I would go back and change it, but I'm not. You're stuck with me making those small mistakes. Sorry. All right, so for SST, this is based upon the treatments. How many treatments do we have? We have P in total, so our degrees of freedom are P minus 1. So to calculate MST, we just take that SST divided by P minus 1. We are done. We have the average for our treatments. Same idea for our blocks. We have B blocks in total, so B minus 1 is our degrees of freedom. The one that becomes a little bit more tricky, but not really more tricky, but it's the sum of squares for the error. So remember, we have a total of P times B observations that we are going to get returned to us. That's going to be the number of calculations that we have. So our degrees of freedom in this case is P minus 1 times B minus 1. And just a quick note here, this MSE is still the point estimate for the common variance. So that is still our sigma squared. All right, so now let's look at that test statistic. So we're going to get a test statistic that's going to help us determine whether or not we are going to reject the null hypothesis or fail to reject the null hypothesis, all based upon the alpha and our critical value. But we need our test statistic first to determine, are we to the left of the critical value or to the right of the critical value? So our test statistics is just dividing out these averages that we just calculated here. And the MSE, the error that's on the bottom, is still going to be that big one here. So the MSE is our denominator for each. For the treatments, we have MST on top, and for blocks, we have MSB. So again, really, where is this kind of difference helping us in terms of this compared to when we didn't have that one-way ANOVA? So remember, our total beforehand just came from factor plus error. So our factor was our between treatment variability, our error is within treatment variability. Now, if we did have this inherent bias, our error would be larger. And this is, of course, what we are dividing out by when we're looking at these test statistics, is always dividing out by the MSE. So the larger the error, the larger the denominator, the smaller the overall ratio, the less likely we are going to reject the null hypothesis. But what we're doing here is we're still taking the total. That hasn't changed. We're still taking the factor. That hasn't changed. But what we're doing now is we are breaking up this error. We're breaking it up into things that we know. One of the things that we know is, again, the blocks. And after that, there is the error. There is the part that I just don't know. So this is error sub 1. And these two together is what forms here. So I'm trying to break up this error in terms of, again, something that I know, this inherent bias. Is it real? Well, if it's real, then the block part of this, or the MSB, will have some weight to it. And if it does, then again, it's going to reduce that error overall. So if I have a larger error here, I can reduce that error by, again, separating into these two different components. So that's why we look at, our F statistic for the blocks, because we're going to ask the question, was it appropriate really to set up a design in this sort of way? Is there really a difference between these experimental units, or in our case, is there a difference in these, is there a difference in these blocks, or in our case, because a block is represented by a single experimental unit, is there a difference in these experimental units? There we go. So putting this all together gets us our ANOVA table. Again, if you are reading this from the R output, we don't have this last total line, and we're going to have that last column, which is going to give us our p-values for each one. So we can find the critical values, and if our F statistics are greater than our critical values here, then we reject the null hypothesis, or our starting alpha, if our p-value is less than our alpha, then again, we reject that null hypothesis, meaning exactly the same thing. So what we are looking to do, again, finding that somewhat of a distribution here. It's a horrible looking distribution, but we'll go with it. This is under the assumption that the null is true, that H naught is in fact true. So if we were to run this experiment and there was really no difference in the outcomes based upon the treatments, then we find off, well, what's the last alpha percent of that tail? Where do those extreme values fall in? And if we fall into that critical value range, or past that critical value range into that last little 5% or alpha percent of the tail, then we're going to say, well, no, this is too extreme. Even though it is possible, it's just too extreme. We're going to reject the null hypothesis and accept the alternative. Otherwise, if you fall into this area, the non-rejection region, happy face, I don't know if it's really a happy face because it doesn't give us enough to reject the null hypothesis, but, sounding like it's not being rejected is, maybe that sounds good. Who knows? Trailing off here. But if we fall into that region, we're obviously not going to reject the null hypothesis, because if we're saying that, for 95% of the time or whatever it is, we should expect to see these types of results. And if we did see those results, then, oh, okay, well, I guess maybe the null hypothesis is true. We're not saying that. Sorry. Correction. We just don't have enough evidence to say that it's not true. So we fail to reject. We never say someone is innocent, just not guilty. That's it. All right, so what we want to do for exercise 2 is we want to be able to compute the ANOVA table. We'll do this in just a couple minutes. We're going to do this inside of R. I'm going to have to bring a couple things in, so I'll show you at that point in time. And then we'll go through the different steps here. Actually, just going to jump ahead for just a quick second. Yeah, actually, let's build the ANOVA table. Let's jump over to R, because we haven't done that yet today, and we're already 33 minutes in, and if you haven't seen code within 33 minutes, I've done something wrong. All right, screen number 2. Here we go. Hopefully you can see this. That doesn't look too small, so hopefully this will work out. If not, always send me an email going, let's try and make the screen a little bit bigger, or make myself a little bit smaller. Who really needs to see me anyways? You're here for the code. You're here for the slides. Not here for me. But if you're here for me, thank you. All right, lesson 2. These codes are already posted on Brightspace. Download them. One thing that's going to be different in here is we're going to start by bringing in our data. So beforehand, we didn't do that. In lesson number 1, we created our, again, as I said, they were data frames, but we created like these Excel spreadsheets where we created each one of the columns, put it all together, and that's where our data lied. So we're going to do similar sort of things. We're going to take a spreadsheet kind of setup. We're going to bring that in, and we're still going to create the data frame. Just again, we are going to be bringing outside information, which we haven't done beforehand. All right, so the first thing that we want to do, starting on line number 5. Actually, we don't need this one. We don't need this one to the second half of this, but we'll load it in anyways. We're going to need ggplot because we are going to be able to, what we want to do is sort of visualize some things that are happening in here. And excuse me, ggplot is much better, or sometimes much more control. There we go. So let's load that. We want to load something from the library. We're just using that library function. The input inside of those round brackets, it's the double quotations, and that's the name of what we're trying to bring in, which is ggplot2. All right, so that's loading. That's in. We are good to go. So let's go down to line 14. So what we are going to do, we're going to bring the data in. So what I'm going to use is this read.csv. So right now, if you're on Brightspace, you'll see keyboard.csv. That's the data file that we are in fact bringing in. So I'm going to go read.csv. Now, what I am not going to do is I'm not going to do anything. I'm just going to run this line and we're going to see what happens. Oh, it worked. I was hoping this was going to fail, but it did not fail. This example failed me. Okay, so what you may see in the console that you're going to get an error message when trying to bring this data file in. Why is that? Because what I've done here is I've said, let's use this function read.csv and my input. Again, so inside of those round brackets, that first input that I'm bringing in is called keyboard.csv. It's in the double quotations. So what this is going to do is I'm telling R, use this function, call this file. But I didn't say where to look for this file. This file might be on my computer somewhere. It might not. I might not have even downloaded that, and that might also be a problem there. But the thing is, I haven't told it where it should look. So I need to do, what I need to do is set what's known as a working directory. Let R know, unless I'm giving the full path, unless I'm saying this is in the C drive, under my Windows folder, under my users, or blah, 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 it's going to be somewhere. Unless I'm putting a direct path to it, if I just call it, R needs to know where to look. So I need to do, what I need to do is set a working directory. And I can do that in a couple of different ways, but the easiest way is just right up at the top here. Under Session, I go to Set Working Directory. Now, I can choose the directory that I have this stored in. Now, when I'm doing these sort of things, what I like to do is I like to keep my script files, my data files, again, all in the same spot, just to make things nice and easy. The larger the project, obviously, you may want to have more things separated by different folders, just to keep the organization there. But for things simple as this, I just put everything into a single folder. So what I do again is, so I keep my R files, all of my data files, same folder. So what I simply do to set my working directory is I go to the very top here. I use the source file location. What is my source file? My source file is the R script that I am currently working on. So that's lesson number 2. So if I click this, what it's going to do is it's going to say, and you can see down in the bottom of my console here, set WD. This is set working directory, and it's setting it to c:/users/Gary/downloads/lesson2. So I have a folder in my downloads called lesson 2, which all of this information is set there. That is now set to my working directory. So if I'm asking R, open this file, it's going to go to that directory first and look at, is this file in there? And if I get an error, it's because it's looking somewhere where that file doesn't exist. So if you're working on multiple different lessons here, you could be on lesson 1, you could be on lesson 3, lesson 10, who knows? You're on some lesson here. If you tried to select the wrong working directory and ask it to open something, it's just not going to know where to look. So we need to set that. That's already done. It already knows. It's pulled all that information. So model input 1 is where everything's stored to. So I have 12 observations in 3 variables. Let's just print this to the screen. So again, if I want to be able to see any of my objects that I've created here, so this is being stored as a data frame, I just write the name of the variable I assigned it to. And again, I assigned it using that arrow notation. So read.csv inputs into model input 1. So if I write model input 1, run this from the console, I have my 12 different observations. So I have my block 1, my treatments A, B, and C, and my outcomes for each one. So 77 words per minute, 67 words per minute, 63 words per minute. Then I have my block 2, or again, in this case, my second data entry specialist, A, B, and C, again, the keyboards, and 71, 62, and 59. So on and so forth. So all the information is there. So I have my P different treatments. I have my, so P in this case is my keyboards. So 3 keyboards. I have a total of 4 blocks. So 4 times 3 gives me 12, which is the number of lines that I have here. All right, so now let's build this ANOVA table. Before I build that ANOVA table, again, same as before, I just want to make sure that my columns are in fact correct. Now, if I go up to my global environment, so my top right here, if I open this up for a second, we'll see that I have a column called block, a column called treatment, and a column called outcome, exactly what we have here. Block is an integer, treatment is a character, outcome is an integer. Okay, I want to keep outcome as an integer because it is an integer outcome that we're going to want. But block and treatment, these are categorical variables. They have different levels. I need to make sure that I convert these properly. So again, what I did beforehand is I used that factor function. So what I'm doing here is I can take a data frame. I can take an Excel spreadsheet. I can focus on one column and I can replace that one column. And that's exactly what I'm doing here. So I'm saying model input 1, this is the name of my spreadsheet, or in this case, my data frame. I want to go to the column called block. That's my first column. And I'm going to replace this by, well, again, exactly that same column. But this time I'm running that column through the factor function, which is just going to convert it into a categorical variable. And I'm going to do the second thing, or the same thing for the second column, which is, again, labeled as treatment. So if I execute these two, notice what happens in my upper right corner here. So I have block and treatment. These are now factors. So block has 4 levels, if I could read properly. 4 levels. Levels 1, 2, 3, and 4. Those are my keyboard programmers or my data entry specialists. And treatment has 3 factors, which is the different keyboards A, B, and C. Now notice if I output the data again, nothing has changed. It's exactly the same, but now R knows that these columns are categorical variables with different levels. It just guarantees us most of the time when we're doing this, it's automatically going to know, but I do need to be careful because block was in fact an integer, so it may get confused thinking that that is a second factor. It's not a second factor overall. Well, it's not even that's the second factor, sorry. It's going to think that it is a numerical variable, which it is in fact not, and then it might try and do something that's a little bit weird. So in this case, it's always better just to make sure that we convert these things to categorical variables, so when we run this, we run it properly. All right, so now we want to build the ANOVA table. So again, using the AOV function, the first thing that I'm going to input is that formula. So how do we break this down? Again, we have our outcomes, which is our treatments, the outcome of the experiments. So that outcome column is explained by the treatments plus the blocks, and then there's going to be the error, but we don't include that into our formula. So the data is coming from model input 1. So if I run this and ask for the summary, whoops, there's my ANOVA table down at the bottom. So I see that first my sources of variation are my treatments, blocks, residuals. That's my error. I have DF for my degrees of freedom. So treatments, there's three treatments in total. So 3 minus 1 gives me 2. That's my degrees of freedom. The blocks, 4 minus 1 gives me 3, which is the degrees of freedom for the blocks. And the residual is 2 times 3, which gives me 6. So everything is there. I have my sum of squares already calculated. Now kind of notice this. The block and the residual, we are roughly sitting around 146. So if we didn't do this, if we kept this as a one-way ANOVA, the block would be, or the combination of block and residuals would be the error as beforehand, and that would be 146. But now what we've been able to do is break this into 2 parts, one that we can explain and one that we can't. We can explain the blocks, we can't explain the errors. And the blocks contain the vast majority of that. It's 143.6 is its sum of squares, and 2.7 is the error term. So that is a significant difference in breaking up these 2 things. All right, so we have the mean sum of squares for each, so just dividing by the degrees of freedom. We have the F statistics and the P values for each one of these. All right, so let's jump back to our other screen here. So we've created the ANOVA table. Now what we want to do is we want to run the hypothesis test. So the first thing, of course, would be to state the null and alternative hypothesis for each one. We want to compute the F statistic. R has already done that for us. We want to determine that critical value. So where is that threshold for that last 5% or alpha percent of the tail? And if, of course, our F statistic falls to the right of that critical value, we reject the null and accept the alternative. We can also do the same thing for the p-value. And this works exactly the same way. Now do note that there is a different critical value for the blocks than there is for the treatments, because it's all based upon those degrees of freedom. The degrees of freedom are slightly different. For one, it's p minus 1 is our first attribute for it, or parameter for it, and then b minus 1 is the other. So it's going to give us a slightly different distribution. All right, so for the two parts here, what we want to do is we want to be able to run the null and hypothesis, or we want to test the null hypothesis and we want to test the null hypothesis that no difference exists between the effects of the keyboard brand. So again, that primary factor here, and we're setting alpha to be 0.5. And then we're going to do the same thing as before, but this time around for the blocks. So let's look at A here. Our null hypothesis is, this is for the keyboard, so there's 3 different brands of keyboards, A, B, and C. So we'll say mu sub A is equal to mu sub B is equal to mu sub C. So it doesn't matter what brand of keyboard, the average number of words per minute is going to be the same, versus the alternative, at least one differs. Our alpha, again, this is 0.05. Our F statistic, well, we get this right off of R. So our F statistic for the treatment was 441.8. Now remember, the closer this is to 0 or 1, the more likely the null hypothesis is correct. The farther away this is, the less likely that null hypothesis is correct. So this is definitely much farther away, but again, we don't know what that critical value is. So we need to find CV. So let's jump back to R for a second. So let's look at the first one. Yeah, so I've got that here. Let's look at this distribution. So I'm going to just kind of quickly plot this for a second. So this is based upon the treatment. So I want to build a F distribution with degrees of freedom 2 and 6. So 2 being the p minus 1 and 6 being the 2 times I3. And this is what our distribution here looks like. This is, again, under the assumption that the null is true, so that there is no difference between them. So I'm looking, where is that last alpha, which alpha in this case is 5%, where is that last 5% of my tail? Because I'm saying, again, under normal circumstances, if everything was if the true population parameters of each one of these different keyboards were the same, again, it doesn't matter, then if we run this experiment, this is where we should see the average number, or sorry, this is where we should see those F statistics lying. So what I'm doing here is, again, I'm using that QF function. I'm saying I want that last 5% on an F distribution with parameters 2 and 6, and I want the lower tail to be equal to false because I want this to be the extreme right. So that's 5.14. So my critical value, you can see on the screen above here, so 5.14. Whoops, I didn't want to do that. Let's go back. Go back. There we go. 5.14. Perfect. So what does this tell us? That tells us that our F is greater than our critical value. So we are to the right of that distribution, which means we reject H naught, except HA, again, at alpha 0.05. Hopefully you can see that above. Let's just flip this back over here just for the fun of this. There we go. So our critical value 5.14. So if I look at that distribution, so how all the F statistics are laid out, again, under the assumption that the null hypothesis is true, that last 5% of the extreme values, we should see F values starting at 5.14. We're at 441.8. We are well past that cutoff point. So we reject the null hypothesis and accept the alternative B. Same idea. Our null, this time we're looking at the different data entry specialists. So mu of 1 is equal to mu of 2 is equal to mu of 3, which is equal to mu of 4. So we're saying in this case that it doesn't matter which one we use in terms of data entry specialists, it's all going to give us exactly the same average. So basically, we didn't even really need to do a block design because basically these experimental units are in fact homogeneous. Versus the alternative, at least one differs. Again, looking at, again, same alpha, 0.05. Looking at our output in our ANOVA table, our F statistic this time is 107.1, or sorry, 0.7. And now our critical value, this is going to be a different critical value. I'm just going to run this here. You can see from the screen above. This is going to happen on line 41. So if I run line 41, this gives us a critical value. It spits out to the console of 4.76. So that last 5% of the tail, so the most extreme cases that we would get if the null hypothesis were true, would start with an F statistic of 4.76. We're at 107.7, well past that point. So again, F is greater than CV, reject. H naught, accept. HA. So what this means for part A, it means there is a difference in the keyboard that is being used. One of the keyboards, at least one, we don't know which one, but at least one gives us more words per minute. So one is going to be better. We need to be able to determine which one. Now the next question is, well, was it really necessary to do a block design? And again, our outcome here was we reject that null hypothesis. So that means at least one of the data entry specialists was better than the others. So they added an inherent bias to the experiment. So yes, it does make sense. Now, if we failed to reject the null hypothesis, well, we can still go ahead and we can still test things out. It just means maybe the next time, maybe we won't do a block design. Maybe everything else is perfectly fine. We can do just a completely randomized design, and there would be no issue with that. But in this case, since we did reject that null hypothesis, it is validating the fact that, yes, a randomized block design was appropriate in this case. All right, so the last little bit here, and then we are going to end this up for today, is again just looking at, well, we've made this, or if we've made the decision to reject the null hypothesis and accept the alternative. Again, we don't really care about the block. We do care about the treatment because that tells us there is a difference in the treatment levels that we are adding on. We want to know what that difference is. And again, same idea. We use that Tukey simultaneous confidence interval. So same as the one-way ANOVA, no difference in regards to that one. This is all based upon the studentized range distribution. So I just have the picture of the chart in here. You'll see this in most textbooks. Again, we're using R2 to be able to generate all of this. I would never ask you to memorize all of these sort of things because it's impossible to be able to memorize it all. Well, unless you have that super awesome memory. All right, so the last little bit here is we just want to run that confidence interval. So we've made the assumption at this point in time that one is in fact better than the others. Let's determine which one. So let's jump back to R and we'll run through this last little bit. All right, so going down here, we want to be able to, now I have line 47 and line 48. What is the difference between the two? So the Tukey HSD, my input is just model 1. So this is the same as before. If I were to run this, no difference than what I did in lesson number 1. Notice what happens in the console. I get all the pairwise differences for the treatment. Awesome, I did want that, but also all the pairwise treatments for the blocks. Now, I don't care in terms of blocks and determining which experimental unit, or in this case, which data programming expert or data entry specialist expert, blah, blah, whatever it is better than the other ones. I don't care. All I was doing with this is validating the fact that this was useful to use in this type of experimental design, using this randomized block design. If I failed to reject the null hypothesis, then I didn't need blocks. But I do need blocks. I don't care which block is better. I just needed that block because, again, I wanted to break up that last little bit of variability. So the error before, I want to break it up to newish error, block error. Okay, so if I run line 48 now, which is almost the same thing, except now my input for this function has two inputs. It has model 1, but it also has, well, which column do I want to focus on? In this case, I just want to focus on treatment. So if I focus on treatment, it just spits out the first half of the table. Again, if you printed out the whole thing, it doesn't matter. But in this case, it just makes things a little bit cleaner. All right, so we have a total of 3 different keyboards. So 3 choose 2 still gives us 3. So there's 3 different comparisons that we need to do. So let's look at the first one. B minus A. This is telling us if I replace keyboard A with keyboard B, the difference is going to be minus 10. So there's going to be 10 less words per minute. So replacing A with B, I get a worse outcome. So I get more words with A than what I get with B, and how many more? I get 10. Now, is this always going to be true? Let's look at the lower and upper bound. Remember, this cannot cross 0, because what we're looking for is That negative 10 is the point estimate for the difference between the two because it is based upon the experiment. I want to know, where does that true value lie? Where is that true difference? And if it crosses over 0 from my lower to upper bound, or my upper to lower, it doesn't matter which order I go in. As long as it crosses over 0, one of the possible outcomes is in fact 0, which means it doesn't tell us anything. In this case, my lower bound is negative, my upper bound is negative, so it means regardless, I'm 95% confident that the true difference of replacing A with B is going to give me something that is negative. So A is better than B. And I'll do that up here on my screen, A greater than B in terms of that. All right, so let's look at A and C now. This is my second line. So if I replace keyboard A with keyboard C, again, I get negative. So A is telling me by default, it's better. I'm getting more words per minute than what I would get with keyboard C. But again, I need to look at that lower and upper bound. So my lower bound, negative, upper bound, negative, perfect. Doesn't cross 0. So I'm 95% confident that the true difference between these two keyboards is going to lie somewhere that's negative. So it's telling me that A is better than C. So A is better than B, A is better than C. A is my best keyboard overall. But now can I say something about B and C? Well, my last line here, if I replace B with C, negative. Okay, so B is better than C, but is that true? Well, let's look at that lower and upper bound. Again, negative, negative, it doesn't cross over 0, so we're 95% confident that the true difference between the two is always going to be negative as well. So B is better than C. So if I wanted to put this in order, it would be A, then to B, then to C. And I'm able to tell this, again, based upon that. Now, I don't care about the blocks. I just don't. The blocks do not matter. The blocks are only there, or testing the blocks, we're only there to be able to say, yes, it was appropriate to use a randomized block design. I'm really caring about the keyboards in this case. So that's it. That's all. That's a randomized block design. The next thing that we're going to be doing is two-way ANOVA, and that's going to finish up lesson number 1. So we'll see you back here for the lesson 4 or lecture 4. Until then.